Welcome to your first lecture set. In this lecture, we are going to talk about properties, measurements, and maps of the atmosphere, basically covering chapters 1 through 3. Okay, so for this set of lectures, what I will do, and I'll do this for all the lectures, I like to pose key questions, such as what is the difference between weather and climate? What kind of gases make up the atmosphere? What are some major properties of the atmosphere? How do we measure these properties and map the properties? Also, for each lecture set, I will introduce key terms, but I do not define them necessarily right away. I'll talk about them throughout the lecture. So this is a list of terms, and just as a quick review here, heat and temperature work together. The troposphere is actually a layer in the atmosphere where most of the weather occurs. Pressure and wind are intrinsically related. So are water vapor, dew point, and relative humidity. Now, radiosondes, Doppler radar, and satellites are certain ways that we measure the atmosphere, and a synoptic map is a type of map that we look at where we look at large-scale weather. On the right, you see this really weird-looking cloud. This is a Kelvin-Helmholtz wave. It's a really cool wave, and we usually see this in the upper atmosphere. But in this case, fog, and due to higher winds in the upper atmosphere, created sort of a curl and created a wave-like shape. And I don't think I've ever seen another example of this type of wave or this type of cloud on the surface of the Earth. So what do you think the difference is between weather and climate? A lot of people get these terms mixed up. For example, you might look at a weather event, an event that happened in just one day, and expect that weather to represent what most of the weather is at a certain place. But weather really is just day-to-day fluctuations of the atmosphere, and climate is the long-term pattern of the atmosphere. So I like to think of climate as, a nice sunny beach. When you think of a beach, you usually think of it as being very calm and having really great weather. So climate is like what you typically see. It's the long-term patterns and average weather, and it's also the magnitude and frequency of events. For example, the hottest temperature ever in Woodland Hills, recorded at least, was 119. That was a record high, so that's considered part of climate. Weather is the day-to-day fluctuations of the atmosphere. As you can see here, we have a tornado with a rainbow. We have lightning. We have a hurricane in the lower right. You see the waves splashing onto the coast. So think of weather as short-term and climate as long-term. In this course, we're going to use both weather and climate to talk about severe and hazardous weather. And we'll see the role of climate and how climate change could actually affect severe and hazardous weather in the future. Let's talk about the Earth's atmosphere. And before I give you some, basic facts, take a look at the image on the right. You can kind of see the atmosphere. If you look at this blue line right here, that thin blue area is represented, it is the atmosphere on this image. The atmosphere is quite thick, but the area that would scatter blue light is relatively shallow. So the atmosphere, as you probably already know, is a life-giving phenomenon. It's a great thing to have. Not all planets have atmospheres, or not all celestial bodies have atmosphere. Some spheres like Venus have too many greenhouse gases, and it's not a great place to live. So Earth has a great life-sustaining atmosphere, but that atmosphere is not balanced. Because the sunlight hits the Earth at different intensities, depending on if you're near the tropics or at the poles, we have different energy across the Earth. So in order to try to balance that out, weather occurs. So weather is the process of trying to find a balance between all of the differential heating of our planet. Now, the atmosphere is mostly invisible. So when you're trying to understand the processes of the atmosphere, it's good to know a little bit more about molecules and atoms. Just think of a molecule as a substance that has two or more atoms, and that gives you sort of a tangible view of the atmosphere. Now, the actual molecules that make up our atmosphere is there's about 78% of nitrogen and 21% oxygen. That leaves us with 1% of a lot of other gases. Now, water vapor, which is a greenhouse gas, and we'll talk about water vapor in this lecture, actually can range anywhere from 0 to 4%. We also have other greenhouse gases, carbon dioxide, methane. We have argon, which makes almost 1%. So there's quite a bit of variability in the atmosphere, but at least when it comes to nitrogen and oxygen, that is relatively stable. So now I am listing out the major properties of the atmosphere. And these properties are ones that we're going to come back to at a later time when we start getting into specific severe and hazardous weather events. We need to lay the foundation for understanding those events. Property is temperature. What is temperature? And related to temperature, what is heat and energy? So I have this as a question for you. You probably have examples of energy and maybe an understanding of temperature. It's how hot something is or how cold something is. But what is it on a molecular level or based on physics? So we define energy as the ability to do something, the ability to like push, pull, lift some kind of matter. And in this case, in our class, that matter is in the atmosphere, whether it's atmospheric gases or, rain particles in the atmosphere. Temperature really is just the average internal speed of atoms and molecules. So we're talking internal speed, not how fast like an object is moving, but how fast are the atoms and molecules vibrating. The faster they're moving, the higher the temperature. Heat is a very important energy source within the atmosphere. The sun provides heat and the heat is transferred in different ways. So the definition of heat, basically, as you can see, it's energy, but it's processed or it's being transferred from one object to another. And it's always from a hot object to a cold object, never the other way around. So we have two bubbles of air. You see on the left, we have cold air, and on the right, we have warm air. Remember, temperature means that we have a higher average speed of molecules. And that's what you're seeing in this bubble. The warmer air has a higher speed, so that also means, in most cases, it's less dense. And colder air is more dense. That's going to become really important when we talk about severe thunderstorms. Okay, so on this slide, what we're looking at are ways to measure temperature. We have three ways, 3 units. We live in the United States, and for some reason we still use Fahrenheit, which places 32 as the freezing point and 212 as the boiling point. But scientists like to use Celsius and Kelvin. Celsius is 0 freezing and 100 boiling. With Kelvin, 0 is actually the coldest temperature possible. So the Kelvin is really nice in certain equations. I think for this class, we're just going to stick with Fahrenheit and Celsius. Here we have a map of various weather stations reporting temperature, and we're drawing lines that represent equal temperature. Those lines are called isotherms. So back in the day, this would have to be done by hand, especially if you are a meteorology student. But today, computers can mostly do these kinds of maps. And this shows you a more final version of that map, something that we might display on TV or online. And it just places, colors for each of the 10-degree intervals. And it's a very common way to display temperature. So that's a horizontal look at temperature. If we take a look at the atmosphere vertically, you notice that there's a zigzag pattern of how temperature changes with height. We actually divide the atmosphere up based on how temperature changes. We have the troposphere, and you see in white on the image, the troposphere, the stratosphere, the mesosphere, and the thermosphere. Now, the troposphere contains almost all of our weather, and I'll tell you why it almost contains that. So within just 11 miles, roughly, now that the lid or the top of the troposphere, which is called the tropopause, changes height depending on how warm or cold an area is. But in general, the lowest 11 miles of the atmosphere, temperatures decrease with height, as you probably know if you've gone up into the mountains, and it contains all of our weather, almost. We're going to talk about this later, but the one exception about that is that really severe thunderstorms can temporarily punch a hole into the stratosphere, which is the layer above the troposphere. Because the air is so unstable, we have a lot of vertical movement that can actually get into the stratosphere. This is kind of cool, and we'll see some pictures about that. So we're just going to stick with the troposphere. Maybe in a traditional atmospheric science class, I would talk about all the layers, but we're just going to deal with the troposphere in this class. Okay, let's talk about another very important property of the atmosphere, and that's pressure. And with pressure, we're going to talk about some other types of weather phenomena. Okay, so what I like to do first is talk about a general definition of pressure, because sometimes, even after I've gone through my lectures on pressure, people don't really understand the true definition of just what pressure is. So I like to think of our society. Our society is very high-paced, and let's say you are a student and you are going to school full-time, you are working full-time, raising a family as well. That is a lot of pressure. There are so many different things going on in your life, it almost feels like there's something weighing down on top of you. Well, in addition to that, that's what the atmosphere does. The atmosphere, or pressure, atmospheric pressure, is literally the weight of the air on top of you. So technically, pressure is defined as force divided by an area. For example, the average surface pressure is almost 15 pounds per square inch. Think about that. That's a lot. I don't know if you go to the gym, but think about a 15-pound dumbbell that's sitting on top a tiny square inch of your body. That is a lot. Now, luckily, we live in, our bodies are used to this kind of pressure. When we start going into areas with much less pressure, bad things can happen. So this, we survive this kind of pressure. And there is also some buoyancy forces with air around us and under us. But that is the average pressure. In meteorology, in this class, we're not going to use pounds per square inch per se. We're going to use millibars. So you see here, you see this this term MB. I'm not a very good artist here. MB, that stands for millibars. And our average is 1013.25. And just like temperature, at least in the troposphere, atmospheric pressure decreases as we go up into the atmosphere. And it just keeps on decreasing as we get out to the top of the atmosphere and even outer space. Oh yeah, so this bottle I actually had on an airplane. So as we were descending, we were getting into increasing air pressure, and my empty bottle started to collapse. And that was, that's a direct effect of increasing atmospheric pressure as we were about to land. So here is just another way of looking at pressure. Pressure, is the weight of air molecules. And you notice down here on the right that there's a lot of air molecules close to the ground, but very few higher up. And that's because of gravity. Gravity keeps most of our molecules, most of the atmospheric molecules close to the ground. And also that means air density and air pressure both decrease as you go up into the atmosphere, and it decreases quite rapidly. This is just an example of certain air pressure readings, and in this graphic, I stuck with pounds per square inch. You could see like a place like New York City, which is at sea level, roughly 14.7 pounds per square inch. If you go to the mile-high city of Denver, it's only 12.3 pounds per square inch. If you're in a jet aircraft, you're only 4.5 pounds per square inch. That's why we pressurize airplane cabins, to keep our bodies from, well, it's really the sudden change of pressure that would really do damage to our bodies, but also oxygen. We need a good supply of oxygen. Okay. So in terms of dangerous weather, we don't have, as you know, we don't have a lot of severe and hazardous weather here in Southern California, which is nice. But if you think about it, dangerous weather is always nearby. Imagine for a second that you looked up a forecast and it said it was going to be negative 50 degrees Fahrenheit. It would have 100-knot winds and hardly any oxygen for you to breathe. That is actually close by because that is what it would be like if you went 6 miles above your head. So the next time you are either in an airplane or just walking outside thinking about, wow, it's such great weather here, all you have to do is go 6 miles up and you are in a dangerous weather area. In terms of millibar values, as I said before, 1013.25 is average. A typical deep low pressure system is about 980, and a high pressure system is 1040. These are just typical values. So why is that important? Low pressure systems, as we'll learn later, are the kind that usually bring us storms and rain. High pressure systems often mean clear, calm skies. But in the case of Southern California, if we have a high pressure to our northeast, especially in the wintertime, that could lead to Santa Ana winds, a very special kind of hazardous weather that we see here. The highest pressure ever recorded was due to cold air, and it was 1084 millibars. Cold air doesn't always do that, okay? But in this case, due to the extreme, bitterly cold air in Siberia, we had a very high record of air pressure. And the lowest air pressure we usually see at the surface are in hurricanes or typhoons. So here, typhoon tip, 870 millibars. That's extremely low. So just like isotherms, we map pressure values, and we call those lines of pressure isobars, lines of equal pressure. And later on, we'll talk more about these wind barbs. But you see these, these lines that come out of these circles. Those are weather stations symbolizing wind direction and speed because pressure and wind are intrinsically related. We'll talk more about that, I believe, in chapter 7. So the next property is moisture. Moisture is really important to the atmosphere and to life on Earth. Think about one of the more interesting weather events that we have in Southern California, and that's when it rains. So you can already tell, especially after, a 4 or 5 year drought, that moisture is extremely important to us. So we're going to talk about moisture and related terms like water vapor, relative humidity, and dew point. So we just talked about why moisture is important. And another piece of importance about moisture is the phase changes. We will learn later that changing phase of water can actually fuel certain types of storms. And I want to bring up one of the most common terms that we see in everyday life, and that is relative humidity. In fact, if you go online, look at your weather app, most likely it'll report relative humidity. But what exactly is relative humidity? I actually don't really like using relative humidity because it doesn't really tell you how much moisture there is in the air. And that's what we're going to talk about in a second here. So before we talk about that, we got to review some of the phases of matter. Technically, there are 5 phases of matter. In this course, we're going to just do with 3, solid, liquid, and gas. Ice is the solid form of water, as you guys know, and we just call water water if it's liquid, and we use the term water vapor if it's gas. Now here's an interesting thing. Unlike most substances, the solid version or the solid phase is more dense than the liquid phase. However, for water, ice is actually less dense than liquid water, which is why your ice in your drink will actually float. Now, more importantly, when you change a phase, you're using energy in some way. You're either releasing energy out into the atmosphere or you are absorbing energy. And we'll talk about that later on. So what is, I didn't really define relative humidity yet, but let's take a step back. Absolute humidity, as you can see, is really just how much water vapor we have in the air. Now, if you have hotter temperatures, those temperatures have a greater capacity to quote unquote hold that water vapor. Technically doesn't hold it, but I'm going to keep that analogy because it helps people understand and conceptualize water vapor. And here's another way of thinking about it. Let's say you have a puddle of water somewhere and you have a hairdryer. Now, of course, water and hair dryers don't mix, so don't do that. But let's say you want to evaporate that water. Would you want to use the hot air setting of that hair dryer or the cold air setting of the air dryer? I think most people would say hot air. That would speed up the evaporation because hotter air can hold more water vapor. That concept becomes important with relative humidity. So relative humidity actually has 2 parts. It's how much water there is in the air, okay, just like absolute humidity, compared to what could be in that air depending on the temperature. Now, because it has 2 parts, it's really a fraction or a percentage. 0 meaning that there's, basically no water or vapor in the air. 100% doesn't mean that we have, doesn't necessarily mean we have a lot of moisture in the air. It just means that the air cannot hold any more water vapor anymore, and so we are what's called saturated. And when that occurs, we don't have, we can't add additional water vapor. If we do, it'll turn into liquid. It'll start becoming liquid. And that's important when we talk about rain and snow. So just remember, higher temperatures increase the amount of water vapor that the air can hold. All right, so because we are interested in, eventually talking about some rainstorms and thunderstorms, all of these things have clouds. And I'm going to talk about clouds here in a minute, but just to give you sort of a preview, clouds are not air necessarily. They are comprised mostly of suspended liquid water droplets. The term liquid. Now, how do we get to the liquid phase? We have to have a relative humidity of 100%. There are two ways to do that. We can increase the water vapor in the air. Okay, that happens sometimes. Given that the air temperature doesn't change, that you can add enough water vapor to the air so that you have a relative humidity of 100% and you're saturated. Think about this. If it's cold outside, you might have seen your breath really quickly. Your breath, your mouth actually has, a lot of moisture, but the cold air outside can't hold very much moisture. So if you breathe, you will temporarily see a little, well, basically a cloud, and that's liquid water. Now, the most common way to get relative humidity to increase is to cool the air down. You cool the air down to the point where you find saturation. So here's another way of looking at it. This black circle is the capacity of water vapor. And that depends again on temperature. Because let's say it's 5 p.m. It's pretty warm outside. The blue circle is the actual amount of water vapor, and the empty black circle is the capacity. So if you compare the two, that's about 20%. Now let's go farther or later into the night. Let's say it's 11 p.m. and it's much cooler. But the water vapor, the amount of water vapor we have stays the same, but the black circle gets colder, or I should say smaller because the air got colder. So this is roughly 50%. Now, I don't know, let's say you like to stay up pretty late at night and you notice that it's 5 a.m. Who knows, maybe you're watching this video late at night. And 5 a.m., it's pretty cold, or at least we usually see the coldest temperatures of the day around this time of the day, usually right before sunrise. And notice that the black circle and the blue circle are the same size because the air has cooled down so much that we cannot hold any more water vapor. That black circle is filled in, so we have a 100% relative humidity. We have saturation. And in this case, we can get rain. If this happens up in our atmosphere, higher up, we can get dew on the ground. If it's cold enough, we could get snow or frost, fog, etc. Okay, so think about that last piece I talked about where the actual water vapor content was the same as the capacity. That means we have reached saturation. If you have a thermometer and you figure out what that temperature is when saturation occurs, that's dew point temperature. Or in other words, the temperature to which you must cool something down so that you get 100% relative humidity. And when this occurs, we can get clouds or fog, which again are suspended water droplets. You could also get rain or dew on the ground. Have you ever had a cold glass of water? So if you take a look at the picture in the upper right, have you ever had a cold glass of water and over a period of time it started to have water on top of it? It starts to condensate. Now that water around your glass, is that coming from inside the glass? Hopefully not, and most likely not. It's actually coming from the atmosphere. What you're doing is your cold glass of water is cooling the air around it down. And it happened to cool it all the way down to the dew point temperature. And therefore, liquid water forms. And if you don't have a coaster, you may have ruined that table or whatever. So unfortunately, we don't have a lot of time to talk about different types of clouds. But again, I want to emphasize that clouds, first of all, we have usually You know, sometimes we can have more than 100%, but it's usually 100% relative humidity, and they're liquid water droplets, unless you are dealing with these kinds of clouds, the cirrus types of clouds. Those are actually made up of ice. Now, my favorite cloud, the cumulonimbus cloud, is basically a thunderstorm cloud. And we'll talk a little bit more about that in this lecture and in future lectures. Again, that's my favorite cloud. And speaking of, as you see here, this actually is a piece or a part of the Pierce College weather station. And I'm looking north, and this was a few years ago, and I saw some really tall thunderstorm clouds. And these are cumulonimbus clouds. We'll see a little bit more about that in other pictures. Okay, so one other thing about clouds. So as we know, clouds are made up of suspended liquid water droplets, but those water droplets need something to condense onto. And those particles are called condensation nuclei. And they usually are dust or salt or some kind of particulate matter in the atmosphere. And we have two kinds. We have hygroscopic nuclei, which attract water vapor molecules to condense into liquid, or we have hydrophobic, where they actually repel the water. Now, with the cumulonimbus, I mentioned in two slides ago that we have three types of clouds that are made of ice. Well, the cumulonimbus cloud is the tallest cloud on Earth. And so that means it's going to go way up into the upper part of our troposphere. And up there, we'll have a mixture of ice particles and liquid water. So we do have ice particles in other types of clouds. On the right, what you're seeing is a cumulonimbus that hits the bottom of the stratosphere. And like I said before, troposphere is usually where all of our weather, most of our weather occurs. If the thunderstorm cloud is strong enough, it may actually temporarily exist in the lowest part of the stratosphere. In this picture, you don't see that, but we'll see that in other pictures. Okay, we talked a lot about moisture, and we're going to talk about it again later on. It's very key to any kind of weather, you know, regardless of how severe it is. Wind is another thing. What is wind? You know, have you ever thought about what causes wind? So I like to think about this a little bit. What exactly is wind? I had a friend who was a psychology major, and he learned from somewhere that nobody really knows what causes wind. I'm like, wait a minute, yeah, we do. Wind is really a product of the differences in pressure that we see across the Earth's surface. And we'll talk about that a little bit later. Really clear right now, wind is simply horizontal movement of air. Anytime you have air moving, it's wind. And to give you a little bit more of a preview here, the reason why we have wind is differences in pressure. So basically, you know, you may have like walked into a room in your house once and felt like you felt like some wind coming out of that room. That's because the pressure inside that room is different than the pressure outside of the room. The way we measure wind, and this is the big point right now, is we use an anemometer. So this anemometer right here is from the Pierce College weather station. We also have one on a tower, much higher up, and it measures speed and direction. And we've already seen a few of these, and we'll look at them again. When we record the wind speed and direction, we use wind barbs. Okay, so the next part of our basic foundation for the atmosphere is measuring the vertical atmosphere. It's really important to understand what's happening at the top part of our troposphere because weather there actually trickles down and affects surface weather. So one way that we understand the vertical part of the atmosphere is to release radiosondes or Rawinsondes. They are attached to helium balloons, and the actual radiosonde is that white box-like container that you see. It has a transmitter that gives us data, and it measures temperature, humidity, and pressure. So here's one of those stations in the upper left. It's actually releasing the weather balloon. And on the right, you see the radiosonde. Luckily today we have GPS. Most of these have GPS on them, and so we can track their location. So this is a result of a radiosonde. And as you see, it's tracking various weather elements all the way to the top of the tropopause, actually even beyond the tropopause. So the very first very first variable is dew point, and that's over here on the left, and then we have temperature on the right. Notice right here though, temperature and dew point are on top of each other. That's because that's what happens inside a cloud. When the temperature and dew point temperature are the same, you get a cloud, especially in the mid part of our atmosphere. And we also have wind barbs over here. And if you take a look at this wind barb in particular, you see two long lines coming out of the barb. Each of those lines represents 10 knots. So that is actually a 20-knot wind. It is pointed toward the southwest, so that means we have a southwest wind at 20 knots. We always, and I'll say this again, we always label wind by where it's coming from. How do we measure rain? Well, there are several ways to measure rain. As you probably already know, we have rain gauges, spread all across the country, not just at weather stations, but there's a system of rain gauges that anybody can participate in, and that helps sort of fill in the gaps for rain. The most common is your standard rain gauge, and it's still the most accurate. And it's super easy. You just read how much water there is in this tube, and it tells you how many inches of rain there is. And if you might see this here, it says 1 inch of rain equals 10 inches in the real world. That's because we have all that rain on top funneled into a smaller area. Now, another really common way is measuring it using an automated gauge, a tipping bucket gauge. We actually have both of these at the weather station, but officially the National Weather Service does not like the automated stations. They're not as or automated rain gauges. They're not as accurate as your standard rain gauge. And then we have Doppler radar. So Doppler radar helps fill in the gaps of where we don't have rain gauges, because we obviously don't have rain gauges in every place. Now Doppler radar can tell us where it's raining, but sometimes that rain will evaporate, and so it's not a perfect tool to determine where rain has fallen. But the Doppler effect is part of this, and not only does it measure or assess where rainfall is, but it also assesses the speed of rain or any kind of particle. In fact, that's going to become really important when we talk about tornadoes, because Doppler radar can help us understand where a possible tornado is. And if there's flying debris, we can actually sense or see that flying debris on a radar image. How does Doppler radar work? Well, just in a very basic way, it transmits microwave energy, and if it hits something in a cloud, like what we call it a hygrometeor, so it could be any form of precipitation. It could actually be birds or bugs sometimes, which really can screw up our image. But most of the time, we see the rain, and then it bounces the microwave energy pulse back to the radar, and that estimates the location and speed of that particular rain system. And the result is a map that tells us not just where rain is, but if it's heavy or if it's light. Now, in research, we use radar and computer simulations to look at severe weather. You see this thing that's called an overshooting top? That is the piece of the severe weather that can punch a hole into the stratosphere. That's the piece that we'll talk later on. And is the reason why I say almost all of our weather is in the troposphere, because the overshooting top technically is in the bottom of the stratosphere. These computer simulations mapped onto radar images are used not in everyday forecasting, unfortunately, at least not yet. They're usually used to understand severe weather and to research severe weather. We have to talk about satellites. Satellites are so crucial to meteorology. If we did not have satellites, we would be literally in the dark when it comes to areas over the oceans or in areas that we don't have a lot of settlement. We have satellites that simply just produce black and white images of clouds. We also can use satellites to measure cloud temperature by using infrared sensors. Taller clouds are usually colder. And also another thing when it comes to severe weather, satellites are great in looking at the tropics over the oceans to see if there's going to be any hurricanes. There are two kinds of satellites. You have your geostationary, which are satellites that just sit over one particular region. And we have polar orbiting satellites that we don't really use too much in weather. Geostationary ones are more commonly used. Here's an image, a satellite image. What do you think this is? This was, I'm going to use the term Superstorm Sandy. It was a hurricane. Sandy was a hurricane back in the fall of 2012. I believe it was October, end of October of 2012. But it merged with something called an extratropical cyclone. That's why it's so large. But we can see how large it is because of satellite. We can also look at severe thunderstorms. We can look at a profile, well, not really a perfect profile, but we kind of get a 3D sense of these thunderstorms that I just drew over here on the left. And the really tall areas here, I know they're tall because they really stick out and they have rough edges. Those are thunderstorms. And in fact, although the satellite didn't pick this up, you can still get a really good image of what a tornado would look like from above. Obviously, you don't see the tornado, but you can see what the thunderstorm structure in the cloud structure looks like. And that's really important for future forecasting of severe weather. We also have lightning networks that are capable of detecting lightning strikes. So this is important for real-time lightning strikes. If even in Southern California, I've seen radar images and other radar images that are drawn on top of lightning images showing approaching storms. We also can look at the climate or the climatology of lightning. For example, if you look at the picture here in the upper right, we see, I don't know if you can tell, but Florida has the most lightning of any other state. In fact, I read somewhere that it has more than 100 days of lightning. If you don't like lightning, that's not a place you want to live. But if you don't like lightning and you live here in Southern California, you're in the best place. We have very few lightning days. In fact, based on a different map, we have on average about 5 days of lightning. And that's just here in like the Los Angeles area. If you go up into the mountains of Southern California, you would see more lightning. And worldwide, we typically see the most lightning in the tropics. And that's because of something that we see in the tropical areas around the equator called the intertropical convergence zone. It's that for short is ITCZ, and it helps determine where rainforests are occurring. So it rains a lot near the equator. There's a lot of thunderstorms. So therefore, there's a lot of rainforests. Okay, so I thought this was a good place to talk about our weather station at Pierce College. So this weather station has been in operation since 1949. We have more than 70 years of data. That data is sometimes manual and sometimes automatic. And we use these data to analyze the weather here in Woodland Hills. And we also provide data to other agencies, public agencies like the National Weather Service. It's located right on campus, and most students who are taking meteorology classes will have a chance to visit the station. Now, I'm not sure if that's going to happen with this course because it's an online class, but I'll let you know if we can coordinate something. So we're going to look at a lot of different maps in this class. So on the left, these are symbols for precipitation, and you might see these around mapped weather stations across the country. Don't worry about memorizing all of this. Even I don't have all of this memorized, but just keep in mind that these symbols represent precipitation. And then on the left, I'm sorry, actually on the right, we have another example of a wind barb. So as far as speed, this speed represents 25 knots because there are two longer lines and then one half line. So that's 25 knots. And the main barb here is pointed toward the northwest. So that means the wind is coming from the northwest. Okay, so here we have some examples of weather maps. If you look at map A in the upper left-hand corner, these are raw data from weather stations across North America. Now, not every weather station is on here, but you can see that it includes temperature, dew point, pressure, wind speed, direction, cloud cover, all that stuff. And this is something that we don't necessarily show the public. This is something where we do our analysis. Now, B in the lower right is a pressure map, a sea level pressure map with isobars. C in the upper right, that's a temperature map. We use isotherms. And D in the lower right, you might wonder, what is that? Those are dew point temperatures, and the lines are called isodrosotherms. If you ever visit a meteorologist that works at the National Weather Service, they often have almost 6 monitors for every computer because they have to look at all of these maps at once to try to get a good idea of how the atmosphere is behaving. Sometimes, though, a lot of that data that we just saw will be placed on one map. And that happens a lot when we deal with something called synoptic maps, which is sort of a picture of the large-scale weather. Now, this isn't detailed enough to necessarily show severe and hazardous weather events, but it can help us understand the large-scale patterns that can lead to severe and hazardous weather.